All right, so we proved, so just a recap of where we are at in terms of Kuratowski's theorem. So last week we started proving that if a graph has got no Kuratowski subgraph, remember Kuratowski subgraph is a graph that is a subdivision of K5 or a subdivision of K33. Now, we started proving that if a graph G has got no Kuratowski subgraph, then it has to be planar. Now, our aim is to prove that by contradiction. So we assumed that that there is a graph G that's got no Kuratowski subgraph and is non-planar. Let's suppose there exists such a graph. Now recall that from all those graphs that exist, possibly, we chose G to be the smallest graph, the graph that's minimal with respect to that particular property. In other words, the smallest counterexample that has the property that if we break this graph G up into smaller pieces, my smaller pieces are also not, they're also going to be Kuratowski subgraph free, but they are all going to be planar. Right, so that we choose G such that it has that property, the smallest counterexample. So breaking it up into smaller pieces is going to result in a situation where each one of those smaller pieces is going to be a planar graph, and it's going to be Kuratowski subgraph free. So then we started proving some properties of this particular hypothetical graph G, and we said this graph has to be this graph has to be one connected. And also we proved that the graph must also be two connected. So what we want to start off doing now is we want to prove that this graph is in fact three connected. Right, so you're going to have to remove at least three vertices from the graph for it to be a disconnected graph. Right, so we're going to start off, we're going to take the graph G and, right, and we're going to, again, this graph G is assumed to be the smallest counterexample with respect to the property that it has no Kuratowski subgraph and it is non-planar. Right, so we're going to prove the following. So again, we're going to prove this first claim. We're going to remember G is a non-planar graph, and let's say it is not three connected. So therefore we can find a cut set of cardinality 2, and if we remove these two vertices, again, obviously we're going to get a disconnected graph. And then we're going to just show that there is in fact a component C of G minus xy, such that the induced subgraph on C, together with those two vertices that are removed, together with the edge xy, is non-planar. All right, so let's start off. Suppose G is not three connected, and let xy be a cut set of G. Remember, we proved that G is one connected and it is two connected. So therefore, it is connected, and it does not have a cut set of cardinality 1. So if G is not three connected, it means it must have a cut set of cardinality 2. So we're going to first break it up into two cases. So we're first going to look at the case where x and y are adjacent. Okay, so x and y are adjacent. Okay, now this is roughly what the situation looks like here. So there's my cut set, and you can see basically that right. So we have our components there that result if I remove x and y, and I also just want to point out that for each component that you have, each component must have vertices adjacent to x and to y. Just for your information, because in this case, if this component only has vertices adjacent to x, then I can pretty much go and remove this vertex here, and then it's going to have a cut set of cardinality 1, which is a contradiction. So just note that so that component must have somewhere there a vertex adjacent. It must have a vertex adjacent to x and to y. Right. So let's see what happens in this case. Right, so just a note, we'll just label the components C1 up until CK that I get when I remove the vertex X and Y and all the edges incident with X and Y. We get the new graph. Right, so, so considering the first case then, all right, so now just observe that G prime, which is the subgraph of G induced by the vertices x, y, and the vertices of C1. So what is that subgraph? It's this subgraph, right? So it's all, this notation, right? You'll see this in some textbooks. So that is the graph that you get by taking all the vertices, by taking the vertex x and y, throwing that together with all the vertices in the component C1, and then looking at all the edges between those vertices. That is that encircled subgraph. Now that subgraph obviously has no Kuratowski subgraph because G doesn't have his Kuratowski subgraph, right? And also note that G prime is smaller than G. So what did I say about how did we choose G? G is the smallest graph that has no Kuratowski subgraph but is non-planar. Therefore, any subgraph of G is going to be planar, right? Because G is it's minimal with respect to that property. So therefore. By our choice of G, G prime is planar. And also remember, I just said that G is a proper subgraph of G. All right. So therefore, G prime is definitely planar. All right. So now let's just make another observation. Take the G double prime. Right? There's G double prime. Now what is G double prime? G double prime is the subgraph induced by the vertices x, y, and then by all the vertices of all these components, the remaining components, right? So there we've got that whole graph G double prime. Okay, so you take all the vertices of every component Ci for indices I from 2 running from 2 to k. You take that together with the vertex x and y, and you consider all the edges between only those vertices. That is another proper subgraph of G. So by our choice of G, this G double prime is also going to be planar. Remember, because it is smaller than G. And we said that G is minimal with respect to the property that it's Kuratowski subgraph free and it is non-planar. So every subgraph of this graph G has to be planar. Okay, so considering the graph G prime and G double prime, they are both planar. Right, let's just consider our sketch again. So what I'm going to do is I'm going to take that graph G prime on its own, and I know it's planar. So what does that mean? Well, we're going to discuss that just now because that's an important point. So remember the definition of G double prime. So I'm going to take that section of that graph there and take those two separate graphs next to one another, and I know both of those graphs G. So that is the graph G double prime, and that is the graph G prime. Right, so taking those G and G prime. Right, so if we consider first of all a G prime on its own, we say G prime is planar. Now recall that this edge xy lies on the boundary, on the boundary of some region. Now for any planar graph, we can embed a planar graph in such a way that the edge xy lies on the boundary of that one exterior region that we get. Right, so we perform that folding process that I explained in the last lesson. Okay, so there's a hypothetical representation of G prime. So let's assume the worst case scenario is that that edge lies on a face that lies in the interior region of the planar embedding. So I can just change that by folding everything that lies outside of that face. I can contract it and fold it inwards. Right, so as I explained, you can fold that inwards and get the following representation. There we've got our new representation, and now that edge xy lies on the boundary of the exterior region. So I can do that for G prime, and now if we consider G double prime, there's a representation of G double prime, and in case the edge xy lies on the face of an interior region, whatever lies outside of that face, you can fold it inwards and get the edge xy to lie on the region, on the boundary of the exterior region. Right, so doing that, we get a new representation for G double prime. Right, so then we get our new representation. So that used to be, could possibly be on the in the interior region, and there we have changed it so that it lies on the exterior region. All right, so there we've got our two representations, G prime and G double prime. So what do we do now? We can now go and form a planar graph by doing the following. So what you can now do is you can take G prime and you can pretty much go and embed them, merge them in those two edges, and that graph there, that is a planar graph. Right, so that's a planar representation for the graph G. So that's a contradiction. Okay, so basically, let's just put that in words. As G prime and G double prime are both planar, we can embed both G prime and G double prime in such a way that the edge xy lies on the boundary of the exterior region, whence this will yield a planar embedding of G. Right, as I've illustrated, you put those two embeddings together and you superimpose them and you form a planar embedding for G. Okay, and that is a contradiction. Right, that's a contradiction. Okay, so now we need to consider the second case. That's the case where x is not adjacent to y. Right, so let's look at the second case. That's a case where x and y are not adjacent. Right, so we are going to remove that h there, and now x and y are not adjacent. So what we're going to do is we are just going to join x and y with an artificial edge. Right, so there we've got now the new graph that we formed, and that graph is going to have an artificial edge. All right. Okay, so we construct a new graph G subscript E from G by adding the edge xy. Alright, so we do what we did previously, so you define the graph G prime and G double prime, but the only difference is here you define it within, it's this G prime is a subgraph within the new graph G subscript E. And G prime again is a induced subgraph of the new graph G subscript E. Right, now it's important to note that the graph G prime and G double prime, they both are still smaller than the graph G. They've got fewer edges and they've got a fewer number of vertices. So remember, we chose G to be the smallest counterexample. So that our choice of G is still going to play a part in the planarity of G prime and G double prime. All right, so let's consider two cases. The graph G prime and G double prime have no Kuratowski subgraphs. Right now, because of our choice of G, because G is the smallest counterexample, we have, right, so since G is the smallest counterexample, G prime and G double prime are both planar. Remember, G prime and G double prime are smaller than G, and we assume G prime and G double prime have no Kuratowski subgraphs, so they have to be planar. Because if one of them is non-planar, we're going to find an even smaller counterexample to G. So both of them must be planar. Alright, so again, by the same argument, we can take G prime and we can find a planar embedding for G prime such that the edge xy lies on the boundary of the exterior region. We can do that for both G prime and G double prime. Alright, so there's there we have G prime and G double prime, and now what we can do is, again, you can go and take so you can take G double prime, and you can go and again find a new planar embedding for the graph G subscript E. Okay, and now what we have is we've got a planar graph. We've got a planar embedding for the graph G subscript E. Okay, and all we do now is we can go and delete the edge xy and form the graph G, and that is still going to be a planar embedding for the graph G. Okay, so what can we then say? We can then say that as G prime and G double prime are both planar graphs, we can embed both G prime and G double prime in such a way that the edge xy lies on the boundary of the exterior region. Whence, this will yield a planar embedding for the graph G subscript E. Alright, so that will yield a planar embedding for G, which is a contradiction because we can just delete that edge from the embedding for G subscript E. Alright, so next case is case 2.2, and that is the case where either G prime or G double prime, let's say for argument's sake G prime, has a Kuratowski subgraph. Alright, so let's just quickly look at the graph G prime again. So now we are saying that this that G prime has a Kuratowski subgraph. All right, so let's just for argument's sake assume this Kuratowski subgraph is just the K5. But you can also look at a subdivision of K5 or K33 or a subdivision of K33. So I mean, look, that subgraph, it can't lie, for example, in say C1, because then you know the graph G is going to have a Kuratowski subgraph. So that Kuratowski subgraph can also not only say have X on it, because then G is also going to have a Kuratowski subgraph. And likewise, you can also not have a situation where this Kuratowski subgraph only shares the vertex Y, because again then this G is going to have a Kuratowski subgraph. So the only other option is what needs to happen here is in fact that this hypothetical Kuratowski subgraph in a G prime, that has to share that edge there, right? So it has to share the edge XY. All right, so that should be a hypothetical edge there. That should be the edge XY, and the remaining vertices on this Kuratowski subgraph, they all have to lie within that component C1. Okay, so that's sort of what my graph looks like. Okay, so there's a sketch, a hypothetical sketch for this particular graph G prime. So it has that Kuratowski hypothetical Kuratowski subgraph, and this Kuratowski subgraph, the edge XY must be an edge on this Kuratowski subgraph. All right, so let's just bring the graph G double prime into the picture. There's that section there, right? Now, what we're going to do is we want to visualize what's happening here. Is if you take this new, if you take G double prime, okay, so there it lies somewhere there, right? Okay, so it lies there, and now what we want to visualize is the following. All right, so let's consider the graph G double prime now, and let's just take that edge away for a short while. Now we know that this this graph is G double prime without that edge is still going to be a connected graph, and we know that in a connected graph there always exists a path between any two vertices. So basically we are going to have a path that is hypothetically going to say run from there, and it's going to run through say that component there and get eventually there, and then it is going to end up there, or it could also run through some other component. The point is there's a path on at least three vertices that are going to run from a path that's going to run from X to Y on at least three vertices. All right, now taking that edge back there. And now again, just go back to the graph G prime, and there we have that K5, and now what we go and do is we go back to the original graph G subscript E. So there is that graph there. And what are we seeing here? What are we seeing? Now, if we go and we again take that edge XY away, right? We take that edge away. Then what are we seeing here? We're seeing, first of all, the red graph, and we see that path, that yellow path between X and Y. Now, putting that information all together, what is the red and the yellow graph together? That is a subdivision of K5. And you can easily, obviously see that because this edge, that edge there, used to be there, and now we've deleted it and replaced it with the yellow path. So that is a subdivision of K5. So that is going to be a contradiction, because now we're saying that G has a subdivision of K5 as a subgraph. Okay, so let's put that in words. So observe that the Kuratowski subgraph of G prime must contain the edge E, since otherwise G has a Kuratowski subgraph. Right, so it must contain that edge. Right, so we can also observe, right, so there we also have that that if you look at the graph G double prime without the edge, we know that graph is connected. So therefore there exists an XY path P in G double prime minus the edge E. Right, so what is the implication of that? Right, so therefore, hence, this graph here, first of all, what's that graph? It's the graph with the vertices of G prime, union with the vertices of the path P, and we're looking at this, the subgraph induced by those vertices within the graph G. So going back to our sketch, what that graph that we're talking about, what that graph is going to be, what that graph is going to be is, you can easily see that it's basically going to be this whole section here, right? Excluding that component there. So it's going to be that, it's definitely going to contain that red and yellow graph. Okay, and it's the induced subgraph within G. In other words, it is now, we take that edge that we added initially, the XY edge, we take that edge away. So hence, that graph there has a Kuratowski subgraph. And what can we then say? We can then say that G has also that Kuratowski subgraph, right? So G has a Kuratowski subgraph. Okay, and what can we then say that is clearly a contradiction? A contradiction. Right, so what is the conclusion we can therefore make? Is that this graph that we talked about initially, the graph G, it is a three-connected graph. It has to be a three-connected graph. All right, so let's just look at the recap here. What we've proved so far is that the smallest non-planar graph without a Kuratowski subgraph has to be three-connected. Now, to complete the proof of Kuratowski's theorem, we still have a way to go. We have to prove another thing before we can actually start making inroads. So we need to prove that every, we still need to prove this, that every three-connected graph without a Kuratowski subgraph is planar. Right, now what we need to do is we need to prove that a contraction cannot generate a Kuratowski subgraph. Now, what is a contraction? Let's first of all discuss what we mean by that. Okay, so let's see what contraction means. You have two vertices there. They are adjacent through a red edge, and we're going to contract the red edge. Essentially, we're going to delete the red edge, and we're going to merge those two vertices into one. Now, those two vertices, they have unshared edges, and those unshared edges are going to become the new incident edges with the new vertex that you formed. All right, so the lemma says that you take the graph G, which we know how we chose G. That's a graph with no Kuratowski subgraph, and it's the smallest graph with that property. Then contracting any edge on that graph does not yield a Kuratowski subgraph. So let's just make sure this cannot happen. So they're going to start off with the graph G subscript E, and the graph G subscript E is now the graph that we formed from G by contracting an edge, XY. So we are going to assume for contradiction purposes that there is an edge. The graph G does have an edge such that the contraction yields a Kuratowski subgraph, and let's call that Kuratowski subgraph H. Alright, so how they prove it is you take the vertex VE, and VE is the new vertex that you formed. Remember, you're taking two vertices that share a red edge, and you contract that red edge, and you're merging those two vertices into one. And you call this new vertex V subscript E. So that is the vertex of G subscript E that is obtained by contracting the edge E. Now, if V is not in H, then H is also a subgraph of G, which is a contradiction. Okay, so let's quickly illustrate that. Alright, so there we've got VE, and VE lies outside of H, and now we're retracting it again back to its original form. So we get the graph G, right? And it is clear that the graph G is going to contain a Kuratowski subgraph, which in this case is going to be H. So that's going to be a contradiction because we assume that G does not contain a Kuratowski subgraph. So that vertex VE must lie on the graph H. It must lie on the graph H. Okay, as the vertex VE therefore has to lie on H, and so obviously it cannot have degree 0 or degree 1 in H because Kuratowski subgraph has minimum degree at least 2. So you distinguish between two cases. So VE must either be a degree 2 vertex, or it must be a vertex of degree more than 2. Right. So let's look at the case where VE has degree 2 in H. Alright, so there hypothetically we've got a vertex VE on the graph H and now we're retracting it again to its original form, the red edge. And then we see actually that the graph G has a subdivision of K5 as a subgraph, which is a contradiction. Okay, so in the next case, we need to consider the case where the vertex VE, has degree at least 3. Okay, we just considered the case where it has degree 2. Now, I'm going to just use K5 as an illustration. The argument for K3 is going to be the same. Right, so the first scenario we have is where we can basically see the vertex X as the vertex VE, and then what we have is essentially we are contracting the edge XY, and we're essentially merging the vertex Y with the vertex X, right? So that's the one scenario. Or the other scenario is where essentially neither X nor Y is actually the vertex VE, and we are just contracting and merging. By contracting the edge XY, we are merging both vertices X and Y into the vertex VE. So just an illustration again, where the first scenario is where X is the vertex VE. VE, remember, is a vertex on H that has degree at least 3. So there we've got Y, and we're pretty much contracting the edge X, Y in, and doing that we are merging Y and X. And I mean, that can happen, or we could have a situation where, for example, Y is that vertex there, and then we contract the edge XY, and in doing so we merge the vertex Y into the vertex X. Alright, next we have the second scenario. There we've got neither X nor Y is equal to the vertex VE, and we are contracting XY into a single vertex, which is now VE, and that VE is the vertex on H that has degree at least 3. Alright, considering the first scenario, note that the graph G is going to have K5 or a subdivision of K5 as a subgraph. If we look at that Y and we're contracting or merging Y into X, we see that G is still going to have that whole graph as a subgraph. If we have the other scenario where Y lies there, you can also see immediately G is going to have a subdivision of K5 as a subgraph. And if we merge, if we contract the edge XY, that's just going to give us a K5. So in both cases, G has a subdivision of K5, or G has just the graph K5 as a subgraph. And that is clearly a contradiction. Right, let's look at the second scenario. So that is the case where neither X nor Y is the vertex VE, and we pretty much we contract the edge XY and we merge the vertices XY into the vertex VE. Right, now so here you've got, just to indicate that you could have different situations here. You could have that X is here adjacent to 3 vertices, or X can also be adjacent to 2 vertices and Y adjacent to 2 vertices, as an example. So now the question is, now we can go and inspect deeper and see what is happening in this case. All right, so let's label the vertices as indicated there. All right, so let's partition the partition x1, y1, and y in the blue set, and the other set, the yellow set, contains x, x2, and y2. Now note that this vertex x is adjacent to all the vertices in the blue set, right? Y2 is adjacent to every vertex in the blue set, and x2 is adjacent to every vertex in the blue set. Now also note that y is adjacent to every vertex in the yellow set. y1 is adjacent to every vertex in the yellow set, and the same is true for x1. So what graph is this? Right, so throwing the blue and the yellow together, we get what? We get a K33. So the blue set is the one partite set, okay, and the yellow set is the other partite set. So this is going to imply that the graph G has a K33 as a subgraph, which is a contradiction. Right, let's look at the second sketch there again. You can partition the vertices there in a blue and a yellow set. And again, note that every vertex in the yellow set is adjacent to every vertex in the blue set. And every vertex in the blue set is adjacent to a vertex in the yellow set. So there again we get a K33 with the one partite set being yellow and the other partite set being blue. Right, so let's go back to the notes. We already discussed the various scenarios, so this will go quicker. So now consider the case where VE has degree at least 3 in H. And after expanding E back, X is of degree at least the degree of V in G. Right? Then H is also in G with X replacing VE and Y being a subdivision vertex. This is a contradiction. So this is basically the first scenario where you can see X as VE and you just basically merged Y into X. So here, in this case here, as I illustrated with the little animations, Y either lies, Y could lie outside of that graph, in which case the contraction will lead to a K5, but it will also imply that G will have a K5, or Y could lie in the indicated position on the sketch, and then contracting that edge yields a K5. However, that will imply that G will have a subdivision of K5 as a subgraph. So that is basically the first scenario we looked at. Alright, the second scenario we looked at is this next case. And that's a case where H is a subdivision of K5, and after expanding E back, both X and Y are of degree 3. Okay, so that was the second scenario we looked at. Now, in this case, G contains a K33, which is a contradiction. We illustrated how that works. So again, as I said, in that figure, you can see, you can form two partite sets, and you can see that you have a K33. So what is the moral of the story here? What this lemma basically tells us is that a contraction can never lead to a Kuratowski subgraph. So if a graph doesn't have a Kuratowski subgraph, then a contraction is not going to create one. Right, so I want to emphasize that this very cryptic proof given in the notes, it doesn't cover the case where we deal with K33, and that is, I'm going to leave to you guys as an exercise. But just to illustrate it, there's K33, and for argument's sake, there's the contraction of the red edge. You will have to go and look at the various cases as well. The K33 case is easier to look at than the K5. Right, moving on. So we said now that the graph obtained by contracting the edge is now has a cut set of cardinality 2. So basically we can just make the following statement. So for every edge that you have in the edge set of the graph G, there exists a vertex Z subscript E such that both of the following hold. If you delete VE and ZE, the graph becomes disconnected. And remember, VE is the vertex you get from contracting the edge, XY. And ZE is that other cut vertex we're talking about. And just remember, we said this is a disconnected graph because VEZE is a cut set. Now remember, you can't, if you have a cut set which contains the vertex ZE and some other vertex other than VE, that's going to give a contradiction because that's going to imply that G is not 3 connected. Okay, so this is always going to be a disconnected, and the graph G, take X and Y, delete X and Y and ZE, that's also going to be a disconnected graph. Okay, so that's just expanding VE back into the edge XY. Okay, and that makes sense. Right, so now what we do is we choose the edge E very carefully. So we choose the edge E so that the size of the largest component C of the graph G without X, Y, and ZE is maximized. Right, so we choose E out of all the edges. Remember, we can do this for every edge. Okay, so we just choose the edge E that will maximize the size of the largest component of this graph here. Okay, so now we have this largest component C, and we just let C prime be another component of the graph G minus XYZ E. Now they've given you a sketch here. There you have that vertex Z subscript E, and there you've got those two the two vertices in the remaining two vertices in the cut set. Right, now also just note that there must be an edge F between ZE and a vertex U in Z prime, C prime. So there must be that edge. There must be that edge there. If there is no such edge, that's going to be a contradiction, because then I can delete these two vertices here and the graph G is going to be disconnected. So it's going to contradict the fact that G is a 3 connected. All right, so let's continue. So again, there must be that edge there between those two, between the vertex Z subscript E and a vertex in C prime. Now, by definition, this graph has to be disconnected. Now, what is that graph? It's a graph that I get by deleting this vertex here, okay, deleting the vertex U, right, and deleting Z subscript F. Now what is Z subscript F? Z subscript F is, remember, by definition, what I do, if I contract the edge F, it means I'm merging Z into U. Now Z subscript F is that other cut vertex that we talked about initially, right? When you contract an edge, you merge two vertices into one. The resulting graph is going to have a cut set of cardinality 2, and the Z subscript F is going to be that other cut vertex. Right, so that is going to be a disconnected graph. Now the induced subgraph of C union XY is going to be a connected graph. So what is the graph induced by C union XY? It is pretty much this whole graph here, that graph. All right, so let's just look at why is this graph induced by the vertices C union XY? Why is that connected? All right, so what happens if it's disconnected? Let's pick a component, right? And we pick a component. There's my component, but I pick a component that does not contain that vertex, or that vertex. It's not part of the component that contains both x and y. All right, so the component here lies somewhere in here, but there has to be an edge between a vertex in that component and the vertex z, since otherwise my graph G is going to be disconnected, and that's going to be a contradiction. Right, so if I delete the vertex Z, I'm going to get that disconnected component, which is going to contradict the fact that the graph is 3 connected. All right, so now we know that graph is connected. Also, deleting ZF from this subgraph cannot disconnect it, since this would imply that G without ZEZF is disconnected. Right. All right, so let's just illustrate this. Remember what ZF was. ZF is that other cut vertex that I get once I've contracted the edge F. Now ZF could lie there somewhere in that component there, or it could also lie in that component there. It could also possibly, we'll have to just check that. It could lie in that whole component there. Now the question is, let's say it does lie in this graph C, the graph induced by the vertices C union XY. So let's say it does lie there somewhere. And let's say that when you delete it, that whole component, blue component there, becomes disconnected. Remember, we said here that deleting that ZF from this indicated graph here, we said it cannot disconnect it. Well, let's prove it. Let's say it does disconnect it. All right, so just look at that. There we've got the yellow part and the blue part. Let's just draw it a little bit differently here. Here we've got the blue part, and there we've got the yellow part. Right. Now I want to show that deleting this vertex ZF, let's say that ZF did lie in the blue part. What will happen there? Can it disconnect that graph induced by C union XY? All right, so let's assume that deleting this vertex ZF does disconnect it. So you've got these components here. Okay. Now this the vertices X and Y, they might lie there, or one of them might be ZF and the other one lies in like one of those components there. Right, so in that particular case where we have that, right, so we had those edges between X and Y, we had these edges there. Okay, and they go like that, and if we delete this vertex here, and we delete Z of E, the graph G is definitely going to become disconnected, because we're going to have one of these components here. Right, so by deleting that ZE, we are eliminating all the possible edges here. These edges, don't worry, because they are those ones there. Okay, so that is going to lead to a graph G that is not 3 connected. All right, so let's just check the situation where you have, where say X happens to be, say, ZF, and the Y lies in some other component. Then again, you have your edges there, okay, which are those edges there. You've got that edge there, edge or edges, right? And you've got at least one other component here that doesn't contain Y. Now, if you delete the vertex ZF, which is that vertex there, okay, there, and you delete this vertex here, then again, you're eliminating all these problem edges, and you are going to get that component. You're pretty much going to get a disconnected graph again. So therefore, G is most certainly not going to be 3 connected, so you're going to contradict that fact. So therefore, it follows that G minus ZEZF is going to be disconnected, all right, and the graph G is 3 connected, so that's a contradiction. Okay, let's just go back to our sketch for a short while. Remember, we said G without ZEUZF will be a disconnected graph. Right, so if we delete this vertex, that vertex, and wherever that ZF lies, that's going to be a disconnected graph. Alright, so let's assume what happens if ZF lies there. Now, if you go and delete this vertex here, and that vertex there, basically this whole component we said is going to be connected, right? Okay, so and in addition to that, okay, now remember we said that if you delete ZFZ and you get a disconnected graph. We said C union XY is connected. So what must now happen is this whole graph C prime must become disconnected when we delete Z and U and ZF. So those blue edges indicate those edges between that component and Z and U. Now if you delete Z and U from the graph G is going to become disconnected, and that's going to contradict the fact that the graph is 3 connected. So therefore what we see from here is that ZF can't really lie in C. It can either be Y or X, or it could lie in C prime. Okay, so remember now we said ZF can't lie there. It either lies there, or it lies in this whole graph here. Okay, so okay, so there lies ZF. So what is now the implication of this? If you go and delete that, you're going to form this graph here. Now if you're going to delete that and this vertex here, you are going to get a component, a new component. You're going to get the component C union X, Y. Now remember how we chose the contracted edge E. We chose E such that E maximizes. Remember there, recall, we chose E so that this so that the size of the largest component C is maximized. So in this case, this part, that whole part there is now a component that is larger than C. It contains both X and Y, and that's a contradiction. Okay? So what happens if ZF is, say, X there, right? Then again we're gonna delete this vertex here. We're gonna delete Z and we're gonna delete U, but then we're gonna get a component C, which is going to contain the vertex Y. Well, we're going to get a new component C together with Y, and that is going to be a larger component than C. So that is going to give me a contradiction in both cases, because I'm going to generate a larger component, and that's going to contradict the way we chose originally my edge. So all in all, we can then say that, remember, G without those vertices is disconnected, and it's definitely going to contain a component larger than C, larger than that component there. And that's going to be a contradiction, so that completes